Okay, welcome everybody. My name is Stephen Donnelly. I'm a CTO at Endace. We are a sponsor at SharkFest, and if you'd like to find out more about what we do, you can drop into our channel on Discord and have a chat afterwards. So this talk is called How Long is a Packet? And it's hopefully going to be a fun refresher for some network basics and just talk about some of the concepts that come up in some of the other SharkFest talks, provide a bit of background for that. Okay, let's get started. So, how long is a packet? It would be nice if we could just measure them with perhaps a tape measure. An engineer is likely to say, well, it depends, doesn't it? So, what does the length of a packet actually depend on? Well, we can figure it out. It depends on a few things. The length of a packet is going to be, roughly speaking, the size in bits divided by the bit rate in bits per second, multiplied by the velocity of the signal through the medium that you're sending it through. So those are kind of the parameters, but we need a specific example. So let's talk about a 1 gigabit link. So first of all, let's think about how long is 1 bit in a 1 gigabit network. So 1 bit divided by 1 billion bits per second is how long it takes to send 1 bit, which is 1 nanosecond, very conveniently. And then we need to know what medium we're going to send this through. So for the sake of argument, let's say we're going to send it through an optical fiber. Now, the speed that light propagates in a vacuum is c, speed of light. The speed of light in an optical fiber depends on the refractive index, and it tends to be about 2/3. So the speed of light in a fiber is actually slower than a radio wave. So next time somebody says the Wi-Fi is slow, you can say, well, actually, it's faster than the fiber network. And it turns out that if you calculate that out, the length of 1 bit in an optical fiber at 1 gigabit per second is about 20 centimeters, 0.2 meters, which is about 8 inches, which is the length that we had on the tape measure in the first slide. Okay, but what about an actual packet? So let's say we have a 100 byte packet, 800 bits long, multiply it out, it's 160 meters or 525 feet for the Americans. So it's kind of interesting. So our 100 byte packet is 160 meters long. So that kind of means that if the fiber that you're sending it through is less than 160 meters long, at the time that I'm sending the end of the packet in to the fiber, the beginning of it has already started coming out at the receiver. But if the fiber is longer than, say, 500 feet, say it's 1,000 feet long, then when I'm putting the last bit of the packet into the fiber, none of the bits have come out the other end yet. So there's a short period of time where the packet is stored entirely inside the optical fiber. It doesn't exist in the transmitter anymore, necessarily, and it hasn't been received by the receiver. So we might ask, how much data could you actually store in an optical fiber if you had quite a long one? So let's think about a really long piece of optical fiber. I'm in New Zealand, and SharkFest is at least nominally in California and San Francisco. And if you were to lay a fiber directly between those 2 points, the Great Circle path distance is 10,500 kilometers roughly, or about 6,500 miles. It turns out there actually is a fiber along this path, or at least pretty close to it, although it goes through Hawaii, so it is actually a slightly longer path than that. But this is kind of a good model for how long that could be. So let's imagine that it was a 1 gigabit link. In reality, it's probably a bit faster, but we'll stick with the model. How much data could I write into that fiber before it started coming out in San Francisco? Which is kind of what we're doing with this Zoom session. So it's kind of interesting. So if we sent a gigabit over 10,487 kilometers, run it through the same calculation, we get 52.4 megabits divided by 8 to get bytes. It's about 6.5 megabytes. So as a storage medium, optical fiber is probably not great. Carrying around 10,000 kilometers of optical fiber is a lot less convenient than a USB stick. But how much data could you store if you had a much longer path? Well, let's think about TCP, sorry. So with TCP, the way that it works is I send some data and then I wait for an acknowledgement to come back from the other end of the link. So you imagine our 10,000 kilometer path. It takes 50 milliseconds to send a packet one way and 50 milliseconds to get a packet back the other way. So if I only sent one packet before I waited for an acknowledgement, I'd only get 10 round trips per second. And you can imagine the data rate wouldn't be very good. So how much data am I allowed to send before I have to stop and wait for an acknowledgement? This is something that the receiver advertises called the receive window. And it's the maximum amount of data that I can send before I have to stop and wait for an acknowledgement. And the interesting thing is it's advertised by the receiver. The sender has to hold on to everything that it's going to send because it might not get acknowledgement and may have to resend it. So I have to hold all of that in memory. And if the receive window is very small, as we said, if there's only one packet, for example, the efficiency of the transfer would be very bad. Another interesting point is the sender can't influence the receive window. So there's no way for the sender to say to the receiver, hey, this is inefficient, you need to use a bigger receive window. It's entirely up to the receiver to do that. So how does the receiver know what size it should set the receive window to? So the TCP window, there's a good rule of thumb, which is that you want the TCP window to be 2 times the bandwidth delay product. And the bandwidth delay product is just the number that we calculated before, which is the total amount of data that you can write into the link before it starts to arrive at the other side. So 2 times the bandwidth delay product is enough data to fill the link in both directions. So from the sender to the receiver, and then from the receiver back to the sender. So for our 10,000 kilometer path, that's going to be our 6.5 megabytes that we calculated before, times 2 is about 13 megabytes. Now the TCP window field in the TCP header is only 16 bits long, so it can only represent 0 to 64K. We can't fit our 13 megabytes in there, but there are TCP options, TCP window scaling, which allows you to advertise, to scale that number in order to advertise a larger window. The largest scale factor you can have is 2 to the 14, which means the largest window that you can advertise with the largest scale is about 1 gigabyte. For our example, we need 13 megabytes, so a scale factor of 2 to the 8, which will let us advertise up to 16, would be sufficient for our path. Now, you might wonder, when I last went to a website that was on the other side of the planet, I didn't edit my TCP configuration, right? I didn't go into the operating system and change my receive window. So does that mean that I was doing the internet wrong? And the short answer is, well, there's a couple of answers. One of them is you probably don't expect to get 1 gigabit per second over a single TCP connection from a website that's a very long way away. If you get 2 or 3 megabits per second, you'd probably consider that you've done fairly well. And the second reason is modern OSs support auto-tuning. Rather than allocating 16 megabytes or more for every connection, they start off with a small window, and then they'll increase it in size if they need to. So how large will they increase it to? So Microsoft Windows, relatively modern versions, will auto-tune up to about 16 megabytes, which is enough for our 1 gigabit per second TCP connection over 6,500 miles. Linux is a bit more complicated. I believe it will auto-tune to about 4 megabytes by default in most configurations, most distributions, but it's sufficiently complex depending on versions and distribution. You really need to look that up. You need to Google a TCP tuning guide. So if modern OSs support auto-tuning, why did we just go through all this trouble to work out and describe how to tune TCP, how to set the window size? Well, not everything that's on the internet actually runs a modern OS. There's a lot of IoT devices, Internet of Things devices, embedded systems, cameras, sensors, and so on, which may not have support for auto-tuning. Fortunately, most of those you're probably not trying to do high bandwidth over, so you might get away with it, but it is something worth keeping in mind. Then the other question you might say is auto-tuning sufficient? So different OSs having different limits. What if I want to use a higher bandwidth delay link than what they will support automatically. So with Linux, I might need to tune it manually. Windows, if I have a really long path or I have a really high bandwidth, remember we needed 13 megabytes for our path at 1 gigabit. But if that was a 10 gigabit link, I would need 10 times as much, I'd need 130 megabytes. So what would it look like if we were trying to run TCP over a link with a very high bandwidth delay product? So here is a diagram of the Earth and the Moon. It's to scale. There's the size of the Earth and the Moon and the distance between them. And the point represents a signal traveling at the speed of light from one side to the one location to the other and back. So you can kind of imagine what this would be like if this was a TCP connection. You get SYN, SYN-ACK, ACK with data, 404 not found, reset, reset, and SYN again maybe. So it's going to be a very slow conversation. And the question would be, given that the one-way delay is 1.2, 1.3 seconds, the round trip time is getting close to 2.5 seconds, what bandwidth delay would we get? We need to know what the bandwidth is. So how much bandwidth is there from the Moon to the Earth? Well, there was a satellite launched in 2013, which had a laser communications on it, which could do 622 megabits per second from the Moon to the Earth. So if we ran that through our calculations and said, okay, what's the bandwidth delay product for 622 megabits per second over that distance? It's 99.6 megabytes. So that means that our receive window at the Earth end would need to be set to about 200 megabytes in order to ensure that that wasn't a bottleneck in that link. So it's assuming no packet loss and anything else. So you remember that the maximum window that we can advertise is 1 gigabyte. So that would actually work. You could actually advertise a 200 megabyte window, and in theory, that would actually work. If you rearrange the calculation, you can say, if I did advertise a window of 1 gigabyte, what's the maximum bandwidth I could get on a single TCP connection from the Moon? And it turns out that it's a bit over 3 gigabits per second. So if you're ever on the Moon and you're trying to send more than 3 gigabits per second to Earth, first of all, make sure the receiver has got their window size set correctly. And secondly, you're probably going to need more than one TCP connection. And realistically, you might not use TCP at all for that kind of scenario. All right. So coming back to Earth, we've been talking about packets in a very generic sense. As model packets, but real packets have headers and they have overhead and so on. So let's talk about Ethernet. Ethernet has eaten the world. And if you ask most people, how big is an Ethernet frame? How long is an Ethernet frame? They'll say, well, it's 64 bytes to kind of 15 something something. And this is the IEEE 802.3 Ethernet format, and it is 64 bytes to 1518. And that means that the payload of the Ethernet frame is anywhere from 46 to 1500 bytes. If I only want to send, say, 1 byte of payload, the packet still has to be this minimum length. So the first byte would be my byte, and then the rest of the packet would be filled in with zeros. So it's just padded out with zeros, 45 bytes of zeros, and that would give us our 64 byte frame. But how long is the Ethernet frame actually on the wire when we actually send it? So it turns out there's a bit of overhead with Ethernet, mostly for historical reasons. A typical Ethernet frame will begin with a preamble, which is 7 bytes long, and then a starter frame delimiter, followed by our 64 to 1500. And then at the end, there's an interframe gap where no signal is actually sent necessarily. There's no bytes of data there, but it's essentially a pause, which allows time for switching and routing devices to finish handling the previous frame, if you like. These things were originally invented for networks with collision domains, so CSMA, CD networks. So that means that if we include those extra bytes, there's an extra 20 bytes there. So it increases our minimum frame size to 84 bytes or 1538 for the largest size packet. And if you want to know what's the highest rate of minimum size packets that I can send over an Ethernet link, you'll find that you need to use the 84-byte value, not the 64-byte value, in order to get the right packet rate, because you need to include these preamble and interframe gap times. So that seems pretty straightforward. We're all fairly familiar with Ethernet. It's very popular. And then some people said, look, we like Ethernet so much, we'd actually like to run more than one Ethernet network over the same physical link. We want to run virtual Ethernet LANs over one physical link. But if we include a header in here somewhere in order to tell us which virtual link we're on, then there wouldn't be enough room for our 1500-byte packets. And that would cause problems with interoperability. Can you just make the frame a little bit bigger? And IEEE said, yep, sure. Okay, we'll extend the frame by 4 bytes at the maximum size. So instead of being 1518, it's 1522 plus 4. The maximum Ethernet payload size is still 1500 because we've extended the frame by 4 bytes. The minimum size frame is now, minimum payload is now 42 bytes. So if I'm sending my 1 byte payload, I only need 41 bytes of space to fill that up, and that would still only be 64 bytes long. So that's fine, makes sense. And then telcos came along and they said, look, these VLANs are really great. We like VLANs so much that we would like to use them ourselves, but our customers are also using VLANs. So we kind of need to run VLANs, the customer's VLANs, over the top of our VLAN. So we need another VLAN header, at which point the IEEE folks said, look, you guys are getting a bit ridiculous here. We're not going to keep extending the size of the frame by 4 bytes every time you come back and want to do something. So what we'll do is we'll invent a thing called an envelope frame. So in 802.3, there is now this concept of an envelope frame, which has space for up to 482 bytes of overhead. So you can use this for one or more VLAN headers. You can also use it for MAC layer security, various other extensions or tunnels or LAN emulation, those kinds of things, MPLS, anything you like up to 482 bytes. And they picked this number, which means that the Ethernet frame size at maximum is now 2000 bytes, or if we include the preamble and interframe gap, it's 2020. So 2020, which is kind of coincidental. So now we finally know the maximum size of an Ethernet frame is 2000 bytes. Everybody knows that, right? But Stephen, I hear you say, I'm pretty sure that I've heard of an Ethernet frame that's more than 2000 bytes long. What about these jumbo packets? Aren't they bigger than 2000 bytes? So yeah, there are jumbo packets. They're not standards compliant, so they're not technically 802.3 Ethernet. The reason why the IEEE never adopted jumbo packets as a standard is interoperability. If a packet arrives that's more than 2000 bytes long at an Ethernet switch, and it needs to send it to a client that can't handle packets of that size, the switch can't send a signal back to the sender to say, oh, your packet's too big, you need to make it smaller. There's nothing in the Ethernet signaling specification that lets it do that. And it also can't fragment the packet at the Ethernet layer. The only thing that it can do is drop it. And that's going to cause interoperability problems for various different protocols, which expect Ethernet to deliver a packet without dropping it. The second reason is the checksum. So Ethernet packet, as we saw, has a 4-byte checksum at the end, and that protects against corruption of the packet in transit. So when the packet arrives, we check it against the checksum, and that tells us if there were any errors in it. But the size of the checksum stays the same when a packet gets bigger. So a 64-byte packet has 4 bytes of checksum, 1500 also has 4 bytes. If we made it 9,000 bytes or a megabyte in size, you still only have the same amount of checksum data. So you're diluting that checksum over more and more data. And as you do that with larger frames, the probability of you getting an error which produces the same checksum value, which means you can't detect that there was an error, increases. So FCS weakness is another reason why jumbo packets are not official. You can use them, and people do, typically on a LAN area, so not wide area, and on networks which are very highly reliable, so fiber networks or cable networks where there's very little chance of any corruption occurring. Okay, but this is SharkFest, and we expect to talk about Wireshark. So how does Wireshark report packet lengths when we're looking at packet traces? So this is the inevitable Wireshark live demo part. So you'll have to wait for a moment when we attempt to switch to Wireshark, and we'll see whether that works. Hopefully you can see that on the screen. Tyler can let me know if there's an issue. So here is a packet trace. This is just a general packet trace. I just captured it on my laptop through the wired Ethernet port. There's no crazy Wi-Fi or anything going on here. And immediately when we look at the first packet in the display here, you notice that it's 60 bytes. So wait a minute, didn't I just say that the smallest packet is 64 bytes? So what's going on? Well, one nice thing about Wireshark is you can sort by any column just by clicking on it. So if we click on length, we'll sort by length, we'll find the smallest packet, and make sure I scroll to the top. Yep, so we're at the top. So here's an ARP packet. So it's not an IP packet, it's an address resolution protocol. And Wireshark tells us that it's 42 bytes in length, but that's less than 64. So what's happening? Let's look a bit deeper. In the frame, in the protocol dissection part here, the frame section is information about the packet that Wireshark has been told by the packet capture layer. It's not things which are included in the packet itself. So we can open that up. We can see even in the header, it says that it was 42 bytes on the wire, 336 bits, and 42 bytes captured, 336 bits. So it's not saying that's 42 because it was truncated. It's saying that it really was 42 bytes on the wire, 336 bits. So it sounds pretty confident about that. Those numbers come from two places. There's frame length down here, 42 bytes, and the capture length. Those two numbers come from libpcap. So libpcap or WinPcap in Windows is the packet capture library. And what it's doing is it's reporting what the operating system said the size of the packet is. And the operating system got the length of the packet from the device driver for that network interface. And that got it from the hardware, probably. So everyone in this chain is saying that this packet is 42 bytes long. So let's have a look at it. The Ethernet frame, it does say that it's an Ethernet packet, so we should expect it to be 64. When we click on it, it's highlighting the Ethernet headers, and we've got the ARP part here, and it's definitely showing us less than 64 bytes. Now, one thing that's interesting is we know that Ethernet frames always have a checksum at the end, a frame check, FCS, but we're not seeing that here. It's not showing up in the packet. So what's happened is the packet capture system, probably in hardware, has recognized this packet. It's looked at the checksum, it's checked it, and said, oh yeah, this passes. So you don't need to see the checksum because we already know that it's good. And it recognizes this as being an ARP packet and says, well, this ARP payload is quite short. So rather than giving you the whole packet, I'll just give you the ARP part and you don't need to see the rest. Which is a bit of, a little bit surprising maybe. And if we assume that this packet was 42 bytes in length, then we're going to be underestimating the bandwidth that this packet is using on the link. If you look for the largest packets by searching, reverse searching, and then scroll to the top, the largest packets here are 1514. So this is a TCP frame. And if we scroll to the end once more, we can see there's a TCP payload, but there's no checksum showing up at the end. So the difference between 1514 that we've captured and 1518 that we were expecting is the 4-byte checksum at the end. So no padding on this packet, but there is a checksum that was missing. Okay, so what would happen if we used a packet capture system where we know that it does actually capture the checksum, which I just happen to have conveniently here. So here is a trace file. We're seeing ARP packets again, which we know are fairly short, and they're showing as 64. So we'll just sort by packet length again, descending. Go to the top, whoops, ascending, go to the top. Yep, so the shortest packets in this trace file are definitely 64 bytes. So we click on them. It says 64 bytes on the wire, 512 bits. All of the bytes were captured. And if we click on the Ethernet frame, it's now highlighting two different sections inside the payload. And if we open it up and have a look, we can see it recognizes that the protocol type is ARP. It knows that it's a padded packet, and it was padded with zeros to get to 64 bytes. And it actually, Wireshark will show us the zero padding bytes and highlight them. And it will recognize that there's a checksum present, and it will test the checksum itself in software, even though it's already been done by the hardware, and tells us that the checksum is good. So there's an example of a packet capture that was done with hardware which will capture the checksum for short or long packets, and even for short packets, it will record any of the padding that was there. If we look for long packets in this trace, they're only 600 bytes, so they're not quite as big in this particular one. But again, if we look at the Ethernet frame, we can see there's a checksum, which is showing up at the bottom of the packet down here. So this is the Ethernet checksum. All right. So let's have a look at another case. So here is a different trace file. And this one was captured on a in machine. It was captured on a Windows machine. And looking at it, we immediately see a bit of a problem. The first packet, the length is showing is 2,962 bytes. So again, that's over 1,500 and it's over 2,000. So is it a jumbo packet maybe? Is that what's happening here? Let's sort by length, this time descending to see if we can see what the biggest frames in this trace file are. Scroll up to the top. Okay, so this packet here is 23 kilobytes in size. So it's bigger than 1,500, and it's even bigger than 9,000. So that suggests that it's probably not a jumbo packet. So let's have a look at what Wireshark knows about it first. So Wireshark is saying that the capture layer reported it as being 23K, 185,000 bits on the wire. It seems pretty confident. Let's have a look at the Ethernet frame. Yeah, so Ethernet here, it's not reporting a checksum. So this capture system that we're using here hasn't captured the checksum at the end of the packet. Have a look at the IP layer. So the IP has a total length field, and it's saying that the IP packet is 23K in size. So it's not a error in the capture in the sense. Wireshark is seeing it as being a real 23 kilobyte IP packet. And in fact, it has a TCP payload. If we have a look at TCP, we look at the sequence numbers, we can look at the TCP payload length is also 23K. So by all appearances from Wireshark, this looks like a 23K packet, but we know that Ethernet doesn't do that. So what's going on? What almost certainly happened in this case is this trace file was capturing packets that were being sent and received by the system that was doing the packet capture. And that means that what we're seeing here is TCP segmentation offloads either on receive or transmit. So the idea here is that as far as the OS is concerned, this is a 23K packet, but when it gives it to the device driver to send the packet on the network, the hardware, the driver and the hardware together will segment this out into a number of 1,500 byte packets and send them on the wire. But because of where the PCAP captures the packet in the OS stack, it's before that actually happens. So this one frame that we see in the captured packets was actually multiple packets on the wire, and that's a real trap. And Jesper Bongertz has a good talk about problems when you're doing packet capture. And one of the points that he always makes is don't capture packets on an endpoint system that you're trying to understand the behavior of, because if these offloads are enabled, then you're not going to see the real packets that are on the wire, and you may not be able to understand what's happening. Sometimes if you look this up online, you'll see people suggesting, oh, just turn off all the offloads. So turn off TSO, turn off TRO, all of those things. Now the problem with doing that is that that's going to affect the performance of the link that, or of the system that you're looking at. So the reason we do this is to reduce the packet rate that's arriving at the server. So if you turn those offloads off, the packet rate is going to go up. That's going to put more load on the machine. Your network performance may now be worse than it was before. So you're always better off to tap the network somewhere in the middle with a tap or a span port or a packet broker or something like that. Okay, so I have one more trace, which is what happens if we have a look at some packets that are captured when a packet broker is in use. So what's a packet broker? A packet broker is a piece of equipment that you put into your network, which all of your network links pass through, and it will allow you to filter out some of the traffic and send that off to your packet capture system without having to go in and replug all the cables. Now, I'd like to point out here that this is in no way criticism of packet brokers. They're a great thing. They're very useful. I'll leave the questions to the end. Sorry, I do see you've got a few questions. We'll come back to it at the end if we need to. We can come back to the packet traces. They're very useful devices. So this is not criticism of packet brokers, but let's have a look at what happens here. So we look for short frames. We've got another ARP packet, which we saw before, and normally less than 64 bytes. It's now showing up as 80 bytes. So after going through a packet broker, it's gotten bigger. And the reason for that is the packet broker added a trailer. We can see it down here. So this is a packet trace from an Exablaze Fusion packet broker, which was kindly provided by the Exablaze people. They were happy for me to use this as an example trace in this demo. So let's have a look at what this trailer does for us. So we look at Ethernet. There's the Ethernet header. If we look at the Exablaze trailer, and they've written a Wireshark dissector for it, which is part of standard Wireshark, so it will actually show that for you and dissect it. And it contains a bit of interesting information. So it has a device ID for which packet broker it was and which port on the packet broker the packet was captured on, and the timestamp where it was seen by the packet broker, which might be different to the time that the monitoring system saw it. The trailer itself starts off with the original checksum for the packet. So this being an ARP frame, we can see the Ethernet header, the ARP data, the 0 padding that occurs normally, and then we can see the 4-byte checksum at the end of the original packet, and then we see this new trailer with the device ID on it, the port ID, the timestamp. It's showing up in New Zealand Standard Time because that's the time zone that my Wireshark is running in. And then at the end, there's a new 4-byte checksum for this new Ethernet frame, because the packet broker is an external piece of equipment. It creates a new Ethernet packet to send it to the capture system. Okay, so what effect did that have? Well, when we look at Wireshark, it's reporting this packet as being 80 bytes on the wire, but we know that 16 bytes of that is actually not on the wire. It was on the wire as far as the packet capture system is concerned, but it wasn't on the wire when the packet broker captured the packet originally. So you need to be a little bit aware of, if you were using a packet broker that might be adding a header onto the beginning of the packet or a trailer on the end of the packet, which may or may not be decoded by Wireshark, that will be inflating the size of the packet that's reported here. And if you inflate the size of a packet, you're going to, if you're talking about bandwidth, for example, you're going to see that as being higher bandwidth or higher network utilization than it actually is. So again, nothing wrong with packet brokers. They're very useful and very interesting with the extra information that they provide. You just need to be aware of them when you're looking at those packet lengths. All right, so let's jump back to the slides. Oops. So these slides here are just a recap of what we did in the demo. I'm not going to linger on them too much, but if you're looking at the slide deck later and you don't have the demo available, these slides just cover what we basically talked about in there. Pseudo-headers and so on. And each of these things tends to either make us overestimate or underestimate the length of a packet. That's kind of an important thing. Whereas TCP segmentation makes us underestimate the packet count, so the total number of packets. All right, so let's think about speed a little bit. And we've kind of talked about this a little bit. If you're thinking about the speed of a network link, you're thinking about the throughput that you're getting, and you're looking at Wireshark, you always need to use the length, not the capture length, to avoid underestimating the throughput. Capture systems that don't capture the checksum or the padding for short frames can underestimate the throughput and utilization a bit, but only for small packets, largely. If you include pseudo-headers and trailers, then you're going to overestimate the throughput and utilization on your link. And NIC offloads tend to underestimate the packet rate and count. So you might look at your switch, and your switch might say that it sent 100 packets, and then you look at your adapter statistics on your operating system, and it says it only received 80 packets. So was packets lost, or is it possible that receive offloads just meant that some of those packets were collapsed and delivered together as larger blocks? You also need to think about that a little bit if you're doing provisioning. So if you're trying to work out what bandwidth link do I need to get in order to get a certain throughput. Real networks are not just all small packets or large ones, so there is a bit of a efficiency question here. Bulk file transfers are going to use large packets. Streaming media, voice over IP, financial data feeds, and gaming may use smaller ones. Okay. So MTU mismatch. Let's have a think about this. So far we've been just talking about sending packets over the network and not worrying too much about the length. But MTUs are a real thing. What's an MTU for a start? So the MTU is the maximum transmission unit. Okay, so MTU is what's the largest size packet that can be sent over a particular link, if you like. Different link technologies can have different maximum transmission unit sizes. Not everything is Ethernet. There are other link technologies out there. There are some jumbo packets on Ethernet, even though they're not standard. And various types of encapsulation can reduce the MTU as well. So if I'm tunneling a packet over a VPN, for example, or if I'm using virtualization, mobile IP, those kinds of things, then the MTU is smaller than it would otherwise have been. Now, if an Ethernet switch receives an oversized frame, it can't do anything with it, as we said earlier. It just has to drop the packet. Whereas an IP router can be a bit smarter. So rather than just dropping the packet, it can signal back to the source that there's a problem. So IPv4 fragmentation. IPv4 fragments can be packets, can be fragmented mid-path. So I'm a sender, I send a packet out at say 1500 bytes, it travels through the network through different routers, and it hits a link where the MTU is smaller than that. Then that router can choose to fragment the packet, so chop it up into smaller pieces, continue to send it on. And those fragments will then continue on, and the receiver at the far end is responsible for putting those back together. That's completely transparent to the sender. The sender doesn't know that that's happened, but it's often considered a problem because it increases the CPU load, both on the router that has to do the fragmentation and on the receiver, because it then has to put all these fragments back together. And each of those fragments further on in the network could be lost individually, but you can't acknowledge fragments individually. You have to acknowledge the whole frame. So if one fragment is lost, you can't acknowledge that packet, and the sender has to resend the whole packet, which then gets fragmented again. So it can be quite an inefficient process. If you don't want that to happen, you can set a don't fragment bit on the IPv4 packet. What happens to that router though when a packet arrives which won't fit into the next link in the chain, but it has don't fragment set? So what the router is supposed to do is send an ICMP message back to the source of type destination unreachable with a type message of fragmentation needed, but the don't fragment bit was set. And the sender can then use that to say, okay, that 1500 byte packet was too big. I'll try sending a smaller packet. That's part of path MTU discovery. Now, IPv6 is a little bit different. We do have this thing called IPv6. It's been around for a while now. But it doesn't support mid-path fragmentation by design. So if you're an IPv6 router and a packet arrives that's too large for your next link, for your outgoing link, then you must return an ICMPv6 packet too big message back to the sender. You can't fragment it. It means that there's no don't fragment bit. It's implicit on all IPv6 packets. So that means that the endpoints have to do path MTU discovery. If a higher level protocol can't reduce the size of the message, say it's UDP, say I want to send a 2000 byte UDP packet to some destination, that can't be made smaller. I can't just send 2 UDP packets because it's not the same datagram then. So the IPv6 endpoints can fragment that internally. They can fragment that UDP frame, but that fragmentation occurs end to end. So as far as any of the routers in the middle are concerned, they're just normal IPv6 packets. Okay, we've got a little bit of time. We can have a look at a connectivity problem. So this is a problem from the early internet. And what was happening here is at home, I've got a PC connected to physical Ethernet to an ADSL home router. And I'm connecting to a bank's website. And it works fine. I can browse the bank's website. Everything is perfectly okay. And then I decide that I want to log into my secure internet banking, type in my password, and hit return, and nothing happens. Nothing comes back at all. The link seems to be dead. So what's going on? Now, when we look at these things, they're not all the same, right? So these are all Ethernet except this ADSL one. So let's put the MTUs on. And we can immediately see that the MTU size here is 1492. So it's not the same size as the rest of the links. This is because ADSL at this point was using PPP over Ethernet over ATM encapsulation, and that encapsulation has some overhead which reduces our MTU size. So that shouldn't be a problem, right? Because we've got fragmentation and so on. So when we're communicating with the website, say, the bank's website, if the bank sends a 1500 byte packet down the link, it'll get to the ISP's router and it will say, well, my next hop has an MTU of 1492. I'll have to fragment it. So it fragments the packet, sends the fragments through. The bank never knows about it. We reassemble the fragments to the original 1500 byte packet, no problem. But when I try and log into the secure banking side over SSL, it doesn't work. And why not? So one thing about SSL is that typically don't fragment bit is set in SSL. It's a secure protocol. We don't want it to be fragmented on the network, so we set don't fragment. So when the bank goes to send its response to my login, it sends a 1500 byte packet, it sets don't fragment on it, and it travels through the network and it gets to the ISP's router, and the ISP's router says, well, the next link is small, I need to fragment it. Don't fragment is set. So I will generate an ICMP error message back saying, I need to fragment this, it's too big, but don't fragment was set. So it sends it back to the link, but somehow it doesn't get there. So we can kind of imagine what's probably happening here. The bank's firewall is blocking ICMP. So it drops the packet too large message and it's never received. So as far as the bank's concerned, it sent a packet out and never got an ACK back for it. So the connection just dies. So it's easy to be glib and say, well, don't block ICMP destination unreachable. That would solve this problem. If that happened, then the message would get back to the bank server. They could see that they had sent a too large packet and they could choose a smaller size and then the connection would continue. But unfortunately, that doesn't really help for when I'm trying to log in because I don't have control over the bank's firewall, right? So what I can do though is a thing called MTU pinning. So in this router here, when you think about the home PC, its MTU is 1500 because that's the network that it's connected to. So when it sends a connection request out to the bank, it sends it with an MTU of 1500 that's advertised in a header. When we turn on MTU pinning, the router, looking at that packet as it passes it through, sees the MTU as 1500, but it knows the MTU on the next link is smaller. So what it does is it modifies the packet, it overwrites the MTU with 4092 and passes it through. So when the connection request gets to the bank, the MTU size is set to 4092. It sends a smaller packet back. That packet will traverse all the way through the network. The ISP won't have to fragment it, and it will get through to the end. So today, modern home router devices will typically have that feature enabled. It's something you can check if you're having problems reaching different endpoints. Okay. So to recap, we talked about a few different things. We talked about the length of physical packets on the wire. We talked about bandwidth delay product, or what IETF refer to as long fat networks, and what that means for receiver size, receiver window. We talked about Ethernet frames. We talked about Wireshark and the PCAP, how packet capture works, how different packet capture devices capture and report packets, and what happens if you capture in the wrong place or if you use something like a packet broker, how that affects throughput calculations, and we talked a bit about fragmentation and path MTU discovery, and how that is affected by the maximum packet sizes that you're allowed to send through. So thanks very much. We're a little bit early on time, so we should have some time for some questions. Please do fill in the survey on the app. Let me know if you learned something, would be great. If I got anything wrong, again, let me know that. And if you're an expert and you know all this stuff cold, tell me what you would add to the presentation, what you think I missed if you were asked to give a similar presentation. That would be great. All right, so we'll open for questions. I think there were some questions that came up during the presentation. You there, Tali? Yep.
Yes, I'm here. Tony is asking, Frame 66 has the DF bit set for a 23K packet size. How will the NIC driver chop it up?
Right, okay, so that's a good question. So that was one of our packet traces. Let's go back to Wireshark for a second, and we'll open that trace. That was this one. So we were looking at this 23 kilobyte packet, and we noticed that, where was it in the IP header, where are our flags? Here's the flags here. So here's the flags field in the IP header, and it has don't fragment set on it. So that's a really good question, isn't it? The operating system is sending a large packet, this 23K packet, or 9K in the size, sorry, 2,900 bytes for this one. 23K was the largest packet that we saw, and they have don't fragment set. So how come the NIC driver is able to chop that up into smaller pieces? And the reason is these two mechanisms are operating at different layers within the stack. So when I'm doing a large transmit offset, large segmentation offset, or large receive offset, that's essentially special communication between the operating system and the NIC driver. So even though I've set don't fragment on it, what it means is the NIC driver will still carve this packet up into 1500 byte pieces, for example, if that's its MTU, but it will set don't fragment on each of those pieces. And the operating system will never know that that's happened. It's completely transparent to the OS. The packet will go to the other end and come back, and the network card or the driver will deal with acknowledging the individual pieces separately, and will deal with fragmentation of those pieces if it needs to.
Okay, Ron is asking, so does that mean that with TCP offload, the internal operation of the stack is not compliant with specs for Ethernet prior to offload?
Right, so that's another good question. So Ron's basically asking, these packets here that we're looking at, which are 3K, 23K, though they're over that 2,000 byte limit that IEEE set. So at this point, they're not 802.3 standard compliant packets. But remember, this only occurs inside the PC. So within the server, between the operating system and the device driver, we have these large packets, but they're essentially virtual packets. When they get onto the physical network, if you put a tap in and monitored them, you would only see 1500 byte packets normally, assuming you haven't configured jumbo packets.
Jorg is asking, what about inter-packet gap and preamble when we talk about possible max throughput?
It's a good question too. Okay, so this was going back to the question about the size of Ethernet packets on the wire. We can have a quick look at that slide. Near the beginning. And we were talking about the fact that packets on the wire are slightly bigger than the 1500 byte size that we were talking about. There's this interframe gap and this preamble size. So when I'm sending packets just as fast as I can, one after the other, back to back, this preamble and this interframe gap are still there, even though they're enforced by the hardware, if you like, so they're still there. So when I'm trying to work out what's the maximum number of packets that I can send, what's the highest rate that I can send for a link with a particular bandwidth, you have to include those extra bytes. So if you don't include those bytes, you'll come up with a maximum packet rate, which is different to, which is higher than what you'll actually get on a physical link. Hopefully that answers the question.
Mike is asking, can you talk a little about how fragmentation might cause retransmission and or performance issues?
Okay, yeah, we can do that. So why is fragmentation considered a problem, right? So we have this idea that we have an IP network, IPv4, where we're allowed to have fragments. Why would that cause a problem? So one of the issues is when a router in the middle of a network has to fragment a packet, it's essentially taking one packet, chopping up the payload of that, and then generating multiple packets, which get sent on. So the first packet that gets sent, for example, let's say it was a TCP packet for sake of argument. So the first fragment that gets sent has the TCP header in it. And any downstream router that's looking at that packet will recognize that it's TCP, and it may cache forwarding information based on that flow, for example, on any middleware as well, like load balancers. The following fragment, so that if the second fragment, let's say it was only 8 bytes, that's the tail end of the TCP data, doesn't include a copy of the TCP header. So the router that's doing the fragmentation will generate a new IP header, and it will be, the payload type will be TCP, but there's no TCP header in it. There's just the tail part of the packet. So any downstream router sees the same source and destination addresses, but it doesn't see the same ports, and it won't be able to cache that, that flow, if you like, and do any flow-based acceleration. Secondly, if a fragment gets dropped downstream, because there's some congestion in the network, and we have to drop a certain fragment, the receiver is no longer able to reassemble that whole frame because it's missing one of the pieces. It might be the first piece or the last piece or a piece in the middle, depending on how many fragments there are. So it's going to have to wait. It has to just wait for that fragment to arrive. And eventually it gives up. It has a timeout. And what it will do is it will just acknowledge the previous frame. So it'll continue to acknowledge, I got everything, but I didn't get that last packet you're trying to send. I haven't seen the whole thing. And the sender will eventually say, oh, okay, you didn't get that packet. I'll send it again. I have a timeout and resend the packet. But because it doesn't know that it was fragmented, it'll send it to the same router. The same router will have to fragment it again. And then you run the risk of a fragment being lost again. Hopefully, does that answer the question?
Yeah, that's it for the questions in the Q&A. So I don't know if anyone else has any other questions. We still have a few more minutes.
Yeah, we've got a little bit of time, so if you have a question, feel free to put it into the Zoom Q&A box that pops up at the bottom. If not, I'll be around in the chat in Discord afterwards, and I'll also be available, hopefully during most of SharkFest, in the Endace channel as well, in the sponsor room. But just be aware, because I am based in New Zealand, on the left side of that map that we saw, time zones are a bit out. So although it's, I think, around 5 p.m. In California, it's only about 2 p.m. in New Zealand. So time zones don't always overlap. We'll do the best we can.
Mike says that you learned a lot, and thank you.
Excellent. I'm glad. Please do, you know, take the time, fill in the survey results. Let us know if you learned something. I'd really be interested to hear what you picked up from it, what you found was interesting, or if you have any questions, anything you think I missed. That would be fantastic. Thank you very much. Excellent. Okay. Thank you. All right, Tali. If there's no more questions, I guess we can wrap it up there. And everyone, I hope you enjoy the rest of SharkFest and the rest of the sessions. And I hope that some of the background information here you'll see come up when people talk about bandwidth delay product. People talk about receive windows, and they talk about connection stalling and those kind of things. Hopefully some of the concepts we talked about here will help understand what was happening there.
Thank you.
All right, thank you.